All right, let's talk about valence shell electron pair repulsion theory, or VSEPR. So, VSEPR is basically a way of thinking about how um, atoms form bonds. So, in valence shell electron pair repulsion theory, the bonds within a covalent molecule with covalent bonds are formed from the valence electrons, and that because the lone pairs and the bonds themselves are electrons, which are negatively charged, they repel each other. So what's going to happen is they're going to try to maximize the distance between each other. So the lone pairs want to get away from each other. Okay, so um, lone pairs take up more space than bonding pairs, so the repulsion is maximal between two lone pairs, then between lone pairs and bonding pairs, then between bonding pairs and bonding pairs. So you can see here, turn on my pen. Okay, so you can see that we have our Lewis structure for ammonia, right? And we could also draw that out as an H3 like this. Put a lone pair on the end of the stick. Usually you put a lone pair in a bubble like that. So the idea is, okay, so all four of these bonding pairs and lone pairs are going to try to get as far away from each other as possible. So to do that, they're going to adopt a geometrical structure such that they are maximizing the bond angle between any two components, including the lone pair. So this is what we call the electron geometry. Okay, and then the lone pairs, can't actually see them; they're just electrons. So that gives us what we call the molecular geometry. So let's talk about molecular geometry. So molecular geometry is basically, if you have this many bonding pairs, this many lone pairs, then you're gonna have this shape. So a lone pair and a bonding pair are considered an electron domain. A single, double, and triple bond are each one electron domain. Okay, so this is important. A single bond, a double bond, and a triple bond all equal one electron domain. Okay? So the number of total electron domains, that's lone pairs plus bonding pairs, single, double, or triple, determines the electron pair geometry. Also, might hear me just call it the electron geometry. And then the number of lone pairs determines the molecular geometry. So we'll go through this chart in more detail, but the basic chart is, okay, you have between 2 and 6 electron domains, and that gives you your electron pair geometry: linear, trigonal, planar, tetrahedral, trigonopyramidal, octahedral. Okay. Then based on the number of lone pairs, you have different molecular geometries. So let's go through each of these instances one at a time. So first off, if you have 2 electron domains. Okay. So for example, carbon dioxide, right? You have it there. Why am I drawing it up here? It's already down there. Okay. So again, double bond, that's 1 electron domain. That's 1 electron domain. 1 plus 1 equals 2. Okay. This is called linear. So again, we're maximizing the distance between our 2 bonding pairs. Okay. Maximizing the distance is 180 degrees. Okay. So this is called linear, and you can't put lone pairs on it. Okay. So this is pretty straightforward. It's linear, and the bond angle is 180. Okay. Next up, we have 3 electron domains. This is called trigonal planar. So an example of this is boron trifluoride. Okay, 1, 2, 3 bonding domains, 3 electron domains. Okay, bond angle is 120 degrees. Okay, so this is called trigonal planar. Now here we can't actually put on a lone pair, and we can put it anywhere we want. We put on one lone pair, and this becomes bent, also called angular. So here we have tin chloride. Okay, so SnCl2 has 2 bonds plus a lone pair. So the bond angle here would be less than 120 degrees. Okay, because remember, lone pairs are bigger, so it's going to be squeezing these guys in. Okay, so this one, we call this one angular. Angular is preferred because they're in 4 electron domains, tetrahedral. There's also bent, so we can differentiate those by using different names. Okay, 4 electron domains. 4 electron domains is called tetrahedral. Okay, bond angle is 109.5. So if you have an X, and then you take the top half and you rotate it 90 degrees. Okay, so you have X here, and then one thing coming out towards you, and one thing going back away from you. I'm not good at drawing, but so when this is a good time to bring up when you see a wedge or a dash that's trying to indicate the 3D structure of something in the 2D plane. So a wedge is coming towards you, a dash is going back away from you, a straight line is in the plane of whatever you're looking at, paper or the screen or whatever it is. Okay, the bond angle is 109.5. So if it was just a flat like an X, right, then all the bond angles would be 90. That's not as far apart as we can get away, so we go with 109.5. Okay, we slap on one, so methane, CH4, right? That's an example of that. So methane would be an example of a tetrahedral molecule. Then if you put one lone pair on, you have trigonal pyramidal. So you can see this is a triangle. Whoa, that's not a triangle. So this is a triangle. There we go. A triangle, and it's a pyramid. Okay, so trigonal pyramidal. Bond angle is less than 109.5. Slap another lone pair on, and then we get bent. So this is why we want to call the 3-electron domain, the trigonal planar version, angular to differentiate it from this one. So I'm going to get to the two wacky ones. If we have 5-electron domains, so the way you get here is you access your d orbitals. So these are expanded octets. Okay, so it's called trigonal bipyramidal, and it's got 2 bond angles because it's basically you have a linear that I stuck through a trigonal planar. So I have my triangle here, and then bipyramidal. Okay, so a triangle, 2 pyramids, trigonal bipyramidal. The 3 points on the equator, okay, these are called equatorial. Those are 120 degrees away from each other. And the top and bottom positions, which are called the axial positions, are 90 degrees away from the equatorial positions. Okay, so and the question is, when I put my first lone pair on, does it go to the axial position or does it go to the equatorial position? And it turns out that you go to the equatorial position first because you can push these 2 bonding domains away from you. Okay, so we slap one thing on it and we get what's called seesaw or sawhorse. Okay, so you see it's kind of here, and then this is coming towards you, that's going away from you, so it's kind of it looks like a seesaw. Okay, it's a lone pair up here, right? So the bond angles here would be less than 90, and the bond angle here would be less than 120. Then you have T-shaped. This one's pretty obvious. It's a T. Okay, and this bond angle would be, we just called it less than 90. Reason being is you don't know what exactly the bond angle is going to be is going to depend on the compound, but we know it's going to be smaller. They're going to have smaller bond angles than a seesaw, and that's going to have smaller bond angles than a trigonal bipyramidal. Okay, and then finally we have linear. This isn't a great drawing, but you know, F, Cl, F. And then on the equator, lone pair, lone pair, lone pair, 180 degrees. And finally, we have 6-electron domains. This is called octahedral. It basically looks like a jack. All the bond angles are 90. So sulfur hexafluoride is an example of one, 90 degrees. Everything, all these points are equal. So when you put on one lone pair, it doesn't matter where you put it. And you're going to end up with something that is square pyramidal. Square pyramidal. So we got a square. We got a pyramid. Then we have square planar, so like XEF4 or cisplatin, so square, and it's a plane. So the lone pair goes on the other side because we want to maximize the distance between the 2 lone pairs, right? So it goes on the other side. Then you can also get to T-shaped and linear. So we go to a third lone pair, and we'd have something like this. Right? It'd be T-shaped, and then you get to something like that, right? Or it's linear. I could not find any examples of molecules that have these particular molecular geometries. I looked, I asked ChatGPT. ChatGPT was completely wrong and kept giving me molecules that had 5-electron domains. So I don't know what was going on there. I just couldn't find any examples of this. So if you find an example of this, send me a note. Let me know if you find examples, molecules that fit into this category. Octahedral T-shaped or octahedral linear. I am curious. So these you just need to know this. Okay, so it's good to have. Let me go back to the chart. It's good to have something like this chart. Okay, for practicing, where you can say, okay, I've got this many electron domains and it's got one lone pair, so it's bent. Okay, so you have to know how to draw the Lewis structure. If you can't draw the Lewis structure, you won't be able to use this chart. But then once you draw the Lewis structure, you just follow this chart, and then oh look, it's got 4 electron domains and it's got one lone pair. It's trigonal pyramidal. Okay, so if you follow the chart, you can always find the geometry. So it's a good way to practice. So let's do some practice. Now, again, I'm not going to refer back to the chart. So if you have the chart open on a different screen or print one out in front of you or whatever, I've just done this so many times that I know it. Well, SF6, we already looked at this, but let's go ahead and draw the Lewis structure. So Lewis structure is like that. So I've got 6 bonding domains, right? Which means it's octahedral. And it's got 0 lone pairs, so the molecular geometry is octahedral. ICl2 minus, okay? So we've got iodine. Cl, boink, boink, well, and then I get an extra electron because it's negative. So it's going to be I, Cl, lone pair, lone pair, lone pair. Okay, so I've got 1, 2, 3, 4, 5 electron domains, which is trigonal bipyramidal. Okay, and I've got 3 lone pairs, so that makes it linear. Okay, so this is the basic idea. Then you've got carbon tetrachloride. So carbon, so 1, 2, 3, 4. That's pretty much what it looks like. So 4 electron domains, which makes it tetrahedral. Man, I can't spell today. And then there are 0 lone pairs, so it's tetrahedral. Carbon disulfide is pretty much like carbon dioxide. Okay, remember double bonds are only one electron domain, one electron domain. So 2 electron domains, so it's linear, and that's the only case that you can have there. And then PCl5. Okay, 5 electron domains, so that means it's trigonal bipyramidal, and there's 0 lone pairs, which means the molecular geometry is trigonal bipyramidal. So just remember the so the things to remember are, let me go back to the chart. Okay, so the important things to remember here are that, first of all, you need to be able to draw the Lewis structure, or this doesn't work. Second of all, to remember that lone pairs, that you have your electron pair geometry. If you have 0 lone pairs, then your electron pair geometry and your molecular geometry are the same, right? Linear, trigonal planar, blah, 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 right? Then the molecular geometry is a subset of the electron pair geometry. So tetrahedral, trigonal pyramidal, and bent all have tetrahedral electron pair geometry, but different molecular geometry. So just remember, the electron pair geometry includes lone pairs. The molecular geometry doesn't ignore lone pairs, but you don't see the lone pairs. Like, you don't include the lone pairs when you're thinking about the shape of the molecule, if that makes sense, right? So and that single, double, and triple bonds all count as one electron domain or electron dense area. Okay, so a triple bond. So if you see a linear molecule, those will usually have like a triple bond in it. Usually a trigonal planar will have a double bond in it. Okay, so that's the stuff to be on the lookout for. You could, there's stuff beyond this, but this is pretty much what you need to worry about. You may need to memorize this, but again, regardless, the first step is drawing the Lewis structure. So that you do need to know how to do, and then just to remember that you're counting the number of electron domains. That's lone pair equals 1, single or double or triple bond equals 1.